Okay, welcome back, Physics 20s, to our last lesson in Chapter 7. This is 7.4, and today we're going to be talking about resonance. Today we're going to look at what's the same between swinging on a swing set and breaking a wine glass with your voice. And as you probably could tell from the title of this video, the similarity is they're related to resonance, and that's what we're going to be looking at today in 7.4. So maybe you've seen in a video where a person comes up to a wine glass and then they sing or yell at a certain frequency, those sound waves go out and somehow it ends up breaking the glass. And you might kind of think, how the heck does that happen? Is it a magic trick? Is it something else? I can't see any connection between the person and the glass. How is that actually working? So we're going to explain how that happens. But first I'm going to start with the explanation of a swing set. So if we look at a swing set, it's pretty much the same as a pendulum. We have a mass hanging from a length of rope or chain in this case, and it's going to be a mass swinging back and forth in simple harmonic motion with a certain period and all those other things we've looked at measuring before. I don't have a swing set, but I'm going to model this with a pendulum that I have a computer charger hanging from the roof, so I'll show it with that. Okay, so this pendulum is going to represent our swing set, and just like a swing set or any other pendulum, you pull it back and it swings back and forth in simple harmonic motion with a set period. Now, if this was a person and we're pushing them on a swing set, the goal is to increase the amplitude of this pendulum. So you have to consider when we're going to want to push. If I push really, really quickly like this, nothing really seems to happen. This isn't an efficient way to push someone on a swing set. Same thing if I was going to push them really slow, so we let that happen, and then push there, or infrequent like this. It's just not going to be very efficient. All right, so we need the exact right timing so that this is going to be increasing the amplitude. So first of all, on this side, gravity is pulling it in this direction. And if I'm pushing against gravity, I'm going to be slowing it down. Gravity is accelerating it this way. I don't want to push against that. So I want it to be on this half, all right, on this side. And I want it to be pushing when it's not moving in this direction. I want to be pushing in the direction that it's moving and with the force of gravity moving in that way. I think the easiest place where people mostly push is right here at the endpoint, because the velocity is zero and there's the maximum component of gravity pulling in that direction. So I want to push there and there, and we see that this is a much more efficient way to increase the amplitude. So how often am I pushing? Well, I'm pushing exactly when it comes to the endpoint. The time for when it goes from the endpoint back to the endpoint is one full cycle, which is the same as its period. So as long as I push on the pendulum or the swing at that rate, the amplitude should increase. And that's called its resonant frequency, all right? Its resonant period. How often you're gonna push something so it's gonna increase the amplitude. So let's just pull this back, and it's about 1/1000, all right? About 1 second. I know it's not accurate at all, but about 1 second. So if I push at that rate, 1/1000, 2/1000, 3/1000, 4/1000, we can see that the amplitude starts to get bigger. Now you might think, well, as the amplitude gets bigger, is that going to change the period or how often I have to push it? And we saw from last lesson that this is not going to change. If I release it just the tiniest bit pulled back, 1/1000, compared to all the way back here, 1/1000, it's going to be the same. So imagine I wasn't a person. I couldn't see when it comes back to this endpoint and know when to push it. You could just set up like a robot or something and said, well, just push every 1 second and it's always going to be getting bigger. No matter how the amplitude increases, push every 1 second and it gets bigger and bigger. That is what resonance is. When you're applying something at the right frequency or the right period, and the amplitude gets bigger and bigger and bigger. And again, it's only one set time, one set period of frequency, because if you apply it a lot faster, even if the force is greater, nothing's really going to be happening. So it's about applying a force at the right time, which is the resonant frequency. So how we're going to define resonance is it's increasing the amplitude of an object moving in simple harmonic motion because of a force that's being applied at the object's resonant frequency. So that's really important. The resonant frequency is its natural vibration frequency. So we saw with the pendulum what it naturally swung back and forth at. If we push at that set rate, it's going to increase the amplitude. Now you might be thinking, why am I mentioning frequency so much? Before I've only talked about period, resonant period, but frequency is really closely related to period, and it's related by this formula. F is equal to 1/T, or 1 over period. When we measured period before, this was in seconds per cycle. That's really how long it takes to make one cycle. Now that we're taking 1 divided by that, all it's doing is flipping these units. So now frequency is going to be cycles per second, right? Because we've taken the inverse. So now instead of saying how long it takes to make one cycle, it's to say we have 1 second of time, how many cycles happen in that 1 second. Now for a pendulum, it'd be really small, probably not even a full cycle in a second. But if you have like sound waves or something shaking back and forth really fast, there might be something like 2 full cycles, 10 full cycles, or 100 full cycles just in a second. So it's usually used for things vibrating pretty quickly. So if you ever ask for frequency and you're given period, you just take 1 divided by the period and you'll get the frequency. Now, not just pendulums have a resonant frequency. Anything that when you push and it's going to go to a different spot and come back, that's going to have a resonant frequency. Everything has a resonant frequency. So I want you to look at these blocks first. They're on these wires, and if you push it, they would shake and then come back to their same spot. So I'm going to see if you were to shake this back and forth at different rates, how this would affect it. This video, I'll put the description just here if you want to go watch the full video, but I'll just speed it up here of where it's shaking slowly and all of them are moving, but not too much is necessarily happening. And when we hit this certain frequency right here, they're all being shook the same, except for the ones with the longest wires there. It's pushing it at its resonant frequency right when it comes back to that spot where I kind of showed with the pendulum, where it's going to be pushed and it's in the same direction as the force and it's not going against its velocity. It's going to speed up and it's going to increase its amplitude. So it's just matching that exactly there. We can see it's shaking way more than the other masses. And we can hit those other frequencies. So now we're going to speed up the shaking table and it's going to now hit the one of the middle wire. It has a higher resonant frequency. Now, even though the other one before was resonating at a lower one, it has to match specifically the resonant frequency of that object. So now only the middle one is matched and only the middle one is going to be increasing its amplitude. We got to go really, really fast with the table here as they speed it up and finally get that last mass to shake back and forth at its resonant frequency. And now we're going to explain how this relates to the wine glass. Okay, so instead of pushing with our hand like we did on a swing, we're going to have sound waves or air pressure to be pushing on the wine glass. So this circle here is supposed to represent like looking down on the wine glass. And then you're going to send sound at it. And sound I'm going to draw like this. It's got these circular wave fronts. Now we don't really do waves until chapter 8, but when you make a sound, there's going to be compressions and rarefactions of air. This basically means there's going to be air that's pushing and air that's pulling away. So I'm going to say that these lines right here are going to be pushing. That's going to be where it's moving most. And then there's going to be these areas where it's kind of moving backwards. So you may have seen like a subwoofer that goes back and forth and back and forth. It pushes the air and then it pulls it back. And I think we can use that kind of as a relation for sound here. This is going to be the push. This is going to be the pull that's going to cause things in the shaking back and forth of the air. So when these hit the wine glass, there's an amount of force that is applied to the glass right there from the air pushing into it. Now, it's not a huge amount of force, but it's going to cause it to very, very slightly compress, which this is exaggerated, but it's going to do this. It's going to compress the wine glass. I know not that severe, but that's kind of what's going to happen because of that force. All right. And then when this next the force is gone and it's in that kind of pull part, it's going to go in the opposite direction. Now it's going to be very small at first, but then when it goes back to where it was before, if right at that time our next wave front is going to allow a compression, it's going to be just like pushing that swing at the right time where this is going to build and build amplitude and it's going to compress more and stretch more and it's just going to start to vibrate and getting pushed at the exact right time so it stretches more and more until it breaks. This video can show in slow motion the wine glass bending back and forth and back and forth, and they even do an animation showing the sound waves bouncing off there. This is a video by Marty33, which I'll put kind of the link to that video here. He does a really good job of explaining that. There's also one by Physics Girl that she shows how she learns how to sing and break a wine glass as well. Another good video that you could check out. So that's how I think of relating the two. Pushing the swing the same as pushing that edge of the glass. And if you push it really, really fast, not at the right rate, it's not really going to do anything. But if you hit that perfect timing, the amplitude gets bigger and bigger, and we see the wine glass break or the person on the swing further and further. But how does this relate to examples that you might get asked? there's not really too much more difficult questions than we had from the last day. Now we're just looking at knowing what resonant frequency is and knowing how to calculate it instead of calculating period. So this example says, what is the resonant frequency of a 1.5 kilogram mass on a vertical spring with a spring constant of 40 newtons per meter? Again, everything has a resonant frequency, but we're going to be calculating them for springs and pendulums that we've seen before. So here we have the roof. It's a vertical spring. So we'll draw a spring there connected to a mass, and it's going to go up and down in simple harmonic motion. But if you were to increase this amplitude and kind of be pulling it down or pushing it up, what rate would you have to do that? Well, we have to know that the resonant frequency, which it's asking for, is the same as the natural vibrating frequency of the object, or its natural period. So all I have to do is calculate its period, find the inverse to get frequency, and that's all you have to do for these questions. So we'll start with, for a spring, its period is equal to 2 pi square root of m over k. And again, that's on your formula sheet, so just look it up. And then we're going to solve for t. 2 pi, we just put in our calculator. Make sure you press the pi button, not just 3.14. The mass is already in kilograms, which is good. So 1.5 kilograms divided by K, it's 40 newtons per meter. 40 newtons per meter. And we take the square root, and I'm getting a number there of about 1.216 seconds, right? And remember, that's seconds per cycle, all right? Then just to find frequency, all we have to do now, because this is the calculation that we did from last lesson, is just know that F is equal to 1 over period. So F is equal to 1 divided by 1.216 seconds. And I'm getting a number there of 0.82. 0.82. So that's 0.82 cycles per second, and we're going to write this in the units of hertz, which does mean cycles per second. And that's it. So not a whole lot of new calculating to that, mostly kind of some theory there, but hopefully that lesson made some sense for you. Try the practice questions that I've posted, and I will see you in the next lesson.